Good afternoon, ladies and gentlemen. Welcome to our talk. So today we are going to present efficient and multi-tenant scheduling of big data and AI workloads. Both my colleague Chao Ran and I are senior software engineers at Apple working on big data infrastructure. For example, Apache Spark for offline data processing, Apache Flink for nearline data processing. And we work with Kubernetes in a cloud-native environment. So first, let's take a look at this. What can be some big data and AI use case scenarios, and what can be some intersections of them? For example, we know for AI workflow, it can start from data acquisition and analysis to feature engineering, to model training, to model validation, model deployment, and model inference. And among the whole AI workflow, there can be three very important intersections. For example, the first one, feature engineering. What is feature engineering in essence? We all know that AI engineers can use domain knowledge to abstract features, for example, some properties, attributes, or some characteristics from the raw data. And then they will use these extra feature sets to improve the quality of the machine learning process in order to compare with using the raw data to get better results. After feature engineering, we have model training. So for model training, we know that the AI engineers try to feed the best combination of all attributes they collected into a machine learning algorithm. And why do they do that? They want to identify and learn good values, for example, to minimize a loss function over the prediction range. Another one that is interesting is model inference. Model inference, what does it do? So our AI engineers try to run data points into a trained machine learning model to calculate an output. And it's quite challenging sometimes in a production environment, especially for demanding requirements nowadays. So we take these three as the examples for the intersections of big data and AI. And why do we say that? For example, let's take a look at it here. For feature engineering, model training, and model inference, all of them have real-time and offline use case scenarios. And they can use Apache Spark, Apache Flink, and even more recent frameworks like Ray, etc. So here we say there are the intersections and what can be some challenges and limitations when we look at the traditional big data and AI tech stack. For example, we see a lot of separations, like separate orchestration systems, separate physical clusters to run our AI workloads or data workloads, separate workload scheduling using different frameworks for big data processing, for AI model training, for feature engineering, and also model inference, and separate performance validation, workflow monitoring, using different monitoring pipelines, and try to validate the performance using different frameworks again. And also separate operational routines. Operation can be a headache sometimes. And in this case, we are looking at cloud-native big data and AI tech stack. So cloud-native is a pretty popular term nowadays. Everyone is talking about it. But what is cloud-native in essence? This can be some representative terms that are floating around everywhere, right? Like modern dynamic environment when we try to use public cloud, private cloud, or hybrid cloud. And also containers like Docker containers, and service mesh, where we can try to put different services together and try to utilize them more efficiently, and microservices. And we also have serverless functions, so on and so forth, like immutable infrastructure and clear code deployment. But when we are looking at all of this, what do we want to get from cloud native, and what is our experience with cloud native environment when we are building our infrastructure? So first, we believe that cloud native is about speed and agility. So we know that nowadays, it's very important for new ideas to come to market fast. And in this case, we need to enable our business capabilities to strategic transformation that can accelerate its speed. And our users are actually expect more than before, especially in the production environment. They want innovative features. They also want rapid responsiveness from the infrastructure and our support. And of course, zero downtime. Because performance problems, recurring errors, and also the inability to move fast are no longer acceptable nowadays. Our users will go to their competitors if we're always making mistakes. So in this case, cloud native systems, they are designed to embrace rapid change. And they are designed for large-scale resilience. And the way that we operate them are manageable and observable. So it's very important for our cloud native system to have observability that are easy to manage. And also what is very important is automation. So in a cloud native environment with robust automation, it can allow our developers, our engineers, and also our SREs, DevOps to make high impact changes frequently and predictably with minimal toil. And this is also the reason why that we choose a cloud native environment for our data infrastructure. And what do we use for cloud native? So we use Kubernetes. So Kubernetes, we mentioned about no production downtime in production environment, which is our users' requirements. And in order to achieve that, Kubernetes provides a framework to run distributed system resiliently. What is very important for us from Kubernetes, for example, it can provide service discovery and load balancing out of the box. So we don't need to manage very complicated infrastructure by all ourselves. And can also provide storage orchestration, providing different options for storage and orchestrate them in an efficient way. And also automated rollouts, rollbacks of our service platforms. And self-healing. So we mentioned about users don't want production downtime, but what if our service has some issues, and do we need engineers to manually intervene here and try to scale it back? So Kubernetes comes into the role here to help with self-healing and also secret configuration management, etc. So in essence, we are saying that Kubernetes is not a mere orchestration system. So it is portable, extensible. We can build a lot of customized plugin into Kubernetes, and it can run in different cloud providers, cloud platforms. And it is also open source. So another thing is that we use Kubernetes in a way that to automate our deployment, scaling, and management of containerized applications. So we mentioned about the intersections of big data and AI, and we give the examples of Spark on Kubernetes, Flink on Kubernetes, and for example, Ray on Kubernetes as well. So what are some recent progress of these frameworks on its cloud native support? So for example, Spark on Kubernetes. In Spark 3.1, we have Kubernetes GA, and also Kubernetes enhancement in Spark 3.2, and we've been using them so far. And also GCP Spark on Kubernetes operator. And we also link from GitHub. And for Flink on Kubernetes, this year we have also been making great progress in this area. So Flink Kubernetes has its native integration since Flink 1.11. And we also contributed Apache Flink Kubernetes operator to upstream, and it's released on this April. Okay. And also for Ray on Kubernetes, we have Ray Kubernetes operator and also KubeRay. So then let's take a look at this bigger problem, like resource scheduling on Kubernetes. What can be some challenges and the limitation. So for the first one, we are looking at hierarchical resource queues. So what does this mean? For example, let's say we have a big organization and different teams, and they're running their workloads in the same cluster with different queues, but they need observability on how much resource they're using and what is the minimum, maximum that they can scale up or down to, and what are some other metrics for monitoring. And in this case, what we are looking for is a fine-grained control for different tenants' organization structure. For example, some overcommitment or guaranteed resource that we can provide. The second one is application-aware scheduling. So we know Kubernetes traditionally for scheduling application pods, it doesn't really recognize if these pods belong to a single application. And we are facing this issue, especially when running, for example, batch workloads or streaming applications. How can we make sure that this application can really run without just half of the pods allocated for it, or even the driver pod of Spark only allocated for it, and there can be a deadlock. Another one is mixed workload scheduling. So we are talking about, for example, cost and efficiency, and we want to schedule different workloads in the same cluster to maximize its resource utilization. For example, streaming, batch, AI workload. And how can we better achieve that? And for efficiency and cost saving, because we are running in a cloud-native environment, we want to leverage its elasticity. And in terms of resource fragmentation and also proactively upscaling, when we are looking for more workloads to this cluster, how can we scale up the cluster faster? And how can we make sure that we don't have a lot of resource fragmentation issues when we try to save the cost? And also for central management tooling. So we have mentioned that for observability, it's really important for our operation. But Kubernetes out of the box, it might not provide enough metrics for our operational needs. So what can be some current options for resource scheduling in cloud-native environment? For example, using Kubernetes, we have the default Kubernetes scheduler and runs as part of the control plane, the Kubernetes control plane. And based on that, we also have several other options. For example, Apache YuniKorn. Why do we need Apache YuniKorn? It brings comprehensive resource gathering capabilities and fully compatible with Kubernetes. And my colleague will introduce more on how YuniKorn can help in this case. And we also have KubeBatch. So for KubeBatch, it can provide mechanisms for applications to run batch jobs, leveraging Kubernetes. And also Volcano, which is a cloud-native batch scheduling system for compute-intensive workloads. And last but not the least, there's also the latest queue, which is a set of APIs and controller for job queuing. Then let's look at Apache YuniKorn. So we've been using Apache YuniKorn, and it is a top-level Apache project now. So we officially graduated from the ASF incubator this March. And we are really happy to see the open source 1.0 release, which has major feature release and a big milestone, also this April. And what is also very interesting for us is it is very easy to try out because now it provides a Kubernetes native plugin. So it has more capability with the Kubernetes default scheduler for easy experiment and also adoption. So next, my colleague Charan will deep dive into efficient and multi-tenant scheduling.
Thanks, Chenya. That was a nice overview of cloud-native landscape. But I'm going to dive into one of the core concerns of running cloud-native workloads, that is multi-tenancy. But first things first, let's define some terms. What does it mean to have multi-tenancy, especially in the context of Kubernetes? So I define multi-tenancy as the ability to run workloads belonging to different teams, or what we call tenants, on the same physical environment, or in this case, a physical Kubernetes cluster. Why do we want multi-tenancy? Because we want a more efficient utilization of hardware. by co-locating multiple tenants on the same physical cluster, you have fewer clusters to manage and maintain. That will result in less maintenance workload. So ease of operations is another big plus. But nothing comes for free. In order to reap those benefits, you need to overcome a number of challenges. First and foremost among those challenges are resource sharing between the tenants and also security. Security is a big topic that I'll skip for this talk, and I'll instead focus on the resource sharing part of the multi-tenancy story. So specifically, I'm going to talk about this concept of fairness. So different people have different notions of fairness, but here I'm going to adopt a practical definition. So fairness, I define that as each tenant in a multi-tenant environment being provided with a single tenant experience. In other words, a tenant ideally should be oblivious to the fact that they are sharing the same physical cluster with a number of other people. There shouldn't be any interference between tenants. And similar to Hadoop Yarn, YuniKorn scheduler provides a feature called queues that enable fairness. You can think of queues as a kind of software-defined cluster that users can directly submit jobs to and interact with, so that they don't have to worry about the underlying Kubernetes cluster details. And one of the biggest benefits of using queues for infrastructure providers and maintainers is that we have the flexibility to conduct routine operations like maintenance and upgrade, migration, etc., for the underlying clusters, as long as we maintain the SLOs for users at the queue level, because we can move queues around without disrupting users' experience of using the Kubernetes environment. YuniKorn queues provides a number of nice features, and first among those is quota enforcement. So a queue can have a maximum capacity that you can configure beforehand. What that does is that it limits the maximum amount of resources that all the workloads in the queue may in aggregate consume at any moment in time. Related to that feature is the queuing feature. What that means is that you don't want the workloads to fail simply because the queue is busy. If all the resources are being exhausted right now, you want the incoming workloads to wait there until some resources are released from the queue. That's when you schedule those workloads to run. And also, application awareness is critical to lots of applications that we'll dive deep into in the next 2 slides. But here, it simply means that in your business domain, you might have your notion of what an application means. It could be an Apache Spark application, or it could be a Flink job, it could be a TensorFlow training job, or it could be some other new frameworks that are yet to come. And also, queue hierarchy is something that Chenya touched on in the first section of the talk. So you may want to reflect the organizational structures of your tenant in the queue structure. Last but not least, you want monitoring into what's happening inside the queue. Apache YuniKorn provides a set of rich features, rich metrics that enable you to monitor the usage of the queue in real time. That comes really in handy for our users as well as the infrastructure maintainers, so that you have a real-time visibility into what's happening inside the queue. So now let's talk about application awareness in a bit more detail. As we all know, almost all machine learning or big data applications are multiple units that are distributed across a cluster of machines. It's not just one single Kubernetes pod. It's a whole bunch of stuff that together do some processing to achieve some business logic. The implication of that is during queuing and scheduling, you want to consider all the units belonging to the same application together as a single holistic unit. Consider if we don't do that, what would happen? If we don't have application level awareness during queuing, then that means queuing would happen at the pod level. And what you really don't want that. Because consider this example. You have 2 Spark applications, one submitted right after the other. So now you have 2 Spark drivers that are waiting in the queue, waiting to be allocated. Because there's a delay between the drivers starting and the drivers requesting their respective set of executors, and an executor will be appended to the queue as soon as it is created, it is requested by the driver to the API server. And now what will end up happening is that the queue's layout will be executors from 2 different Spark applications interleaved. And now if you proceed with resource allocation in this scenario, and also if you are operating in a resource-constrained environment, meaning that you don't have sufficient hardware capacity to accommodate all the executors from both Spark applications, then the consequence would be that neither Spark application will be able to run with its full set of executors, hindering performance of both Spark applications. What you really want is that you want to prioritize allocating resources to the first driver only after allocating as much resources as the first driver has requested. If you still have idle capacity, that's when you move forward with allocating resources to the second driver. This is especially important if you have a queue with hundreds of Spark applications. You really want to allocate resources to executors in the same order in which that their respective drivers are allocated. And I was just using Spark as an example. The same reasoning applies to other frameworks as well. So YuniKorn's ordering policy in the queue is really flexible. It's aware of the notion of applications. And you can infuse this knowledge of what an application means by providing custom plugins. So Spark is an example, but in the future, you might have new frameworks coming. You can tell YuniKorn how to identify an application and all the units belonging to that app. So what I just went over was application awareness at a basic level. But there are also scenarios in which you want to enforce a more stringent requirement for application awareness. So introducing GAN scheduling. I should clarify that GAN scheduling is nothing unique to Apache YuniKorn. It's a generic computing concept that simply means that you want to make sure all the resources that are needed by an application are available and ready to use before you allow the application to even start. And I just want to talk about a unique approach that YuniKorn takes in tackling GAN scheduling. So it's done via a simple 4-step process. At the core of this implementation is something called placeholders. So in the first step, YuniKorn reserves the required resources by scheduling what's called placeholder pods. Placeholder pods are nothing but fake pods that are there to reserve the resources that will be needed by the real application later on. And placeholder pods don't really do anything except that they have the same identical specification resource-wise in terms of memory and CPU that are there to be allocated on the node. And second step, after all the placeholders are successfully scheduled, that's when you start the real application. So again, taking Apache Spark as an example, if you have all the placeholders for your required number of executors that have been successfully scheduled, that's when you would allow this driver to start. And the third step is you swap the placeholders with the real application pods when they arrive. Again, in the example of Spark, when the executors are created, which would be maybe a few minutes after the driver has started, the executors will be replacing their corresponding placeholder pods. And the final step is that you have all the resources that you need for the application, then you run it. So the main point of using GAN scheduling is that you want to ensure an acceptable level of performance. Because in some cases, for example, if your Spark application requests 1,000 executors, but the queue has only sufficient capacity for you to run, like, let's say, 2 executors, do you really want your application to proceed? In a lot of cases, the answer is yes, and that's okay. Then you don't have to use GAN scheduling. But in a lot of other cases, you want your application to have good performance. You want at least 500 executors before I would allow my application to start. In that case, that's when GAN scheduling comes in handy. So you might be wondering, why do we go through all that trouble of introducing this placeholder-based mechanism? Why can't we just inspect all the nodes and see whether all the nodes have the available space to host our pods? Why do we need this placeholder thing to reserve stuff? Well, because it's not a very simple answer to get to answer regarding whether we can allocate a specific pod on a specific node. In a lot of cases, even though you have the available resources in terms of memory, CPU, or GPU on a node, it's not guaranteed that your pod will be able to successfully start on that node. A lot of other factors may come into the picture. An example of that would be IP address. Every pod in a Kubernetes cluster, in order for it to start, has to be allocated an IP address. An example scenario that I've run into before was that I've exhausted all the subnets, all the IP addresses available in the subnet in this Kubernetes cluster, and then my pod won't be able to start. And if placeholders can successfully start, that's when you are 100% confident that your real pods will be able to start later on. So placeholders offers strong guarantee that the GAN scheduling will be able to succeed. Also, YuniKorn offers flexible fallback policies. You can either do hard enforcement, which means that if after the initial expiration period, if the GAN requirements cannot be met, then you fail the application. Or another option is to revert to non-GAN scheduling if you want that option. And very importantly, YuniKorn's implementation of GAN scheduling based on placeholders offers very straightforward integration with various frameworks like Spark and Flink using operators, or you can also integrate those with your framework natively. And last but not least, this placeholder mechanism works nicely together with the Kubernetes cluster autoscaler. The reason that you want to run things in cloud is you want to save money, and autoscaling is a convenient way to do that. And cluster autoscaler specifically, it detects the number of pending pods and decides to launch additional nodes to be added to the cluster if there are too many pending pods. And placeholders are there to trigger autoscaling proactively so that it can save time, because it takes some time to add new nodes, to request nodes from your cloud provider, be it AWS or Azure. It takes some time, and placeholders shorten that time for you. So I want to mention another common technique that's used together with autoscaling, and also something that YuniKorn supports nicely. That's called binpacking. Binpacking is something that you do when you want to do aggressive autoscaling. So when you do autoscaling, you really don't want to add new machines if you still have available space in your existing set of nodes. What binpacking does is that when allocating resources to pods, you want to exhaust all the available capacity in the nodes, in your existing nodes, before you look at something else. So binpacking is something that's conveniently defined in this example configuration that I've put on the screen. So it's a what we call a node sorting policy. So when you consider a pod to be allocated on a particular node, YuniKorn needs to sort all the nodes available in the Kubernetes cluster, and binpacking is one of those sorting policies, because you want to pack each node as tightly as possible to exhaust all the space in all the nodes. And you can also define all the weights that in different resource types that you want to consider during this sorting process. So that's lots of nice features that I've talked about, but it's not all those rosy pictures that when you go into the cloud native space. There's a lot of challenges. I want to summarize, I want to conclude with some of the challenges that we've run into. So first of all, Kubernetes control plane has a number of limits. Multi-tenancy is nice. You want to co-locate many users on the same cluster, but it's not always conveniently doable, because a Kubernetes API server, for example, will break down when there are too many nodes in a Kubernetes cluster. And a convenient number will be 1,000. After 1,000 nodes, then lots of things will be really slow or just not work. So at that point, that's when you want to consider having more Kubernetes clusters and doing the same multi-tenancy story on that new Kubernetes cluster. So it will be a trade-off between the number of clusters and number of tenants per cluster. And also binpacking sounds nice. You can save some money. use existing resources as much as possible, but it will also result in node-level performance bottleneck, especially if your application is really compute intensive or uses lots of disk I/O, for example. That will result in some potential job failures. Also, during auto-scaling, a common issue is that you don't have available instance types when you request a particular instance from the cloud provider. That's when mixed instance types and spot instances may come in handy. But those things also have some caveats. For example, spot instances, they are cheap, but they can go away at any with a short notice. Also, application priorities is something that's available in Hadoop Yarn. That's not available in Apache YuniKorn today, but it's on the roadmap. We potentially would need preemption between high priority jobs and low priority jobs. But because of auto-scaling in the cloud, the need for preemption has been made less relevant as it was in the on-premise environment. Last but not least, we need better support for on-premise non-auto-scaling environments. There has been an increasing number of users who adopts Kubernetes in on-premise. For those kind of users, placeholders, Gantt scheduling may need a new design because you don't have auto-scaling. Why do you need pending pods to trigger auto-scaling? So that's a different discussion. So that concludes our talk. Hopefully that was a nice introduction to resource allocation and the cloud native space in general. Hopefully you learned something today, and we have some time for Q&A.
You have some spelled resource. Are you gonna submit a new application in the queue, or your executing application can automatically detect it and using this spell resource?
So if I understand your question correctly, you are saying that when the queue is busy, can you still submit applications?
So sometimes, for example, it's not a peak hour and you are running some offline training and you detect some spell CPU memory nodes that you can use during the off-peak hours. So is that supported that I can submit a new application, or the existing application will be picking up this spell resources?
So you're talking about whether we can use idle capacity when there's machines that are not being used.
Yes.
So yeah, so the way that we avoid waste like that is to configure auto-scaling based on the work patterns. In your specific case, if you have a long period, let's say a few hours a day, during which you don't have much that will be running, then you can configure your auto-scaling threshold to be a really low number, meaning that you don't reserve much capacity during that time. So when you are idle, you don't incur much cost. And you only add nodes when during busy times.
And also for offline applications, we can queue the applications in the queue. So when there's resource, then the application in the queue, which are not running before, can come out and start running during off-peak hours. Yeah. So YuniKorn does provide us queuing functionality.
Okay, that's all time we have for questions. If you guys have any more questions, please reach out to Chen Yan.
Okay, yeah.
Okay.
Thank you.
So much.
All right, thank you.